Okay, so I'm just gonna pick up where we left off yesterday. Does anyone need the notes I handed out yesterday? It's 15.2 today, and then tomorrow we should begin with section 15.3 on triple integrals. Yeah, so where we left off yesterday is we were looking at this theorem 2, that's at the bottom of page 2. This is kind of what you really need to understand, both for this section as well as for sections 15.3 and 15.4 as well. Like this is really like the main way in which we're going to be computing double and triple integrals in this class. So in order to do well on the next exam, you really have to understand what's going on with this theorem. It's really going to make or break whether or not you know how to do these in the first place, pretty much. And so the idea is pretty intuitive. I mean, it really boils down to just working through and practicing through examples enough times until you understand what's going on. But this is kind of like what you're doing every single time when you're computing these double integrals from here onwards. So where we left off last time is we were evaluating this double integral of x squared times y, where the domain, or like the set of inputs, is this shaded in region right here. And so this theorem allows you, it tells you a way in which you can integrate regions that are vertically or horizontally simple, which just means that there's a clear bound. Yeah, there's a clear bound in terms of like what's your upper bound and what's your lower bound. Or if you have like a lower bound with respect to x, i.e. like a leftmost function and then a rightmost function. Okay, and so this is where we're at. And so we set up this integral by interpreting it as a vertically simple region here, which means that we have a lower bound that's always given by 1 over x and an upper bound that's always given by the square root of x. And so what this means is we have that y, the integral corresponding to the variable y, which is this one right here, is bounded below by this 1 over x, i.e. this curve right here. And it's bounded above by the square root of x, which is this curve here. So that's all that's being said with like these upper and lower limits of integration. Like the upper and lower bounds, or the lower and upper bounds, are given by functions of x. And so, like, despite the fact that they're now functions that serve as the upper bounds, the execution really isn't any different. So if we wanted to compute this double integral, we would compute the integral first with respect to the variable y. So this would be equal to the integral from 1 to 3. And then we treat x as a constant. So x squared, you just treat as a number. It's just a constant, and you integrate with respect to y. So this will give you an x squared times 1/2 times y squared. And then this is evaluated from 1 over x to the square root of x. And so you can pull the 1/2 outside of the integral. So this is 1/2 of the integral from 1 to 3 of x squared. And so now all you do is you just plug in the square root of x into y, and then you subtract by that what you get when you plug in 1 over x in for y. So this is going to be times x, or maybe I should write it like this just to make it 100% clear. So this is the square root of x squared minus 1 over x squared dx. Right, all we're doing is just plugging in square root of x into y, 1 over x into y, and we get the following. So this becomes the integral. So it's 1/2 times the integral from 1 to 3 of x squared. The square root of x squared is this x, and then this is going to be minus 1 over x squared dx. And so now we're left with an integral in terms of a single variable, right? So now we're in terms of single variable calculus. You can just apply what you know from single variable calculus. You don't have to do anything fancy here. So this is equal to 1/2. Let's distribute. So this is the integral from 1 to 3. So we have x cubed minus 1 dx. And then if you integrate this, this is going to be 1/2. And then this is going to be x to the 4th power over 4 minus x, and this ranges from 1 to 3. So you plug in x is equal to 3, subtract what you get when you plug in x is equal to 1. So this ends up just being equal to 9, is what the number ends up being equal to. Right, so at least for this function, the computation of the integral itself isn't that bad. It's just a matter of setting things up in the first place, right? Making sure you have the correct bounds of integration. It's really like the setup that we did yesterday that requires thinking. Okay, any questions about this example and how we computed it? Yeah, and so what we're actually doing when we're computing this integral is the following, just to make it clear. So when you're doing double integrals, you should be thinking in terms of volume bounded underneath a curve, right? So what we're doing is we're looking at this region on the XY plane. We're looking at this region that's shaded in the XY plane. I'm not going to do a perfect job of drawing this, but this is the region we're looking at, give or take, right? These are the same two regions. And what we're doing is we're applying F to this region of values on the XY plane, and that'll give us something on the with respect to Z. So maybe like I don't know what this ends up looking like, but maybe it looks something like this up here. And so what we're doing with this integral is we're computing the volume between the actual image. So this is like F of our domain. This is kind of like sloppy math writing, but I'll just say this is like F of our region D. This is our region D. And we're computing the volume between the two. Sorry, I didn't do the greatest job of writing this, but we're really just finding the volume of this like three-dimensional solid between like the image and the domain here. So that's what the integral is giving us. Okay, so like the integral d f of xy, this is equal to this volume between the image or the surface and this region that we have on the xy plane, which is really just the projection downwards onto the xy plane. Okay, so that's what's going on with these double integrals. You should associate it just like we were doing with integrals and single variable calculus as area underneath the curve. Now we're doing it in terms of volume underneath the surface. So even though like we're still looking at these like 2D graphs, like this just means like this is our domain. This is our set of inputs, right? Any questions about this before we move on? Okay, yeah, it's not the best picture ever, but I think it illustrates what you should understand. Okay, this next example illustrates the importance of being able to go between two different kinds of double integrals. So when we were looking at this example, we observed that it was both vertically simple because it has a lower bound and upper bound given by two functions. It was also horizontally simple, right? And that there's not like crossover in terms of what like the upper bound is going to be. It made things a little bit more difficult because the lower bound changes when you pass y is equal to 1. So we went with vertically simple, but you could have done horizontally simple as well. And so we're going to want to make like a reinterpretation of what we're doing. So we want to do like this double integral of e to the y squared. And the main observation is you could note that this is vertically simple, right? The lower bound is always given by this x, like y is equal to x over 2. And the upper bound is always given by y is equal to 2, right? So this is vertically simple because no matter where you start at the bottom, the lower bound is the same and the upper bound is the same. So you can always draw these vertical lines from the bottom to the top. The issue is if we interpret this as being vertically simple, we're left with the following integral, right? If we're doing things such that it's vertically simple, that means we'll be integrating with respect to y, and then we'll be integrating with respect to x. So we'll be looking at the following double integral. So this would be the integral from x over 2 to 2. And then we have that x ranges from 0 to 4. So this would be e to the y squared dy dx. And then we're kind of left with an issue here, right? Because like, I mean, how do you compute the integral of e to the y squared, right? You can't use u substitution. You can't use integration by parts, right? There isn't really anything to play with here. Like if you wanted to compute this integral, you would have to use the Taylor series expansion of e to the y squared. And then, even then, it doesn't have like a well-defined form. Like you can't write it out in terms of like, it's equal to like 2x times e to the y squared. it ends up being like a famous class of, I shouldn't say famous, but like a known like class of functions, right? So you have to do something like this, right? So this is from 0 to 4, x over 2 to 2. You would have to write e to the y squared as the sum from like n is equal to 0 to infinity of y to the 2n over n factorial from calculus 2. And then you would have to integrate this with respect to y, and then you would have to integrate it with respect to x. So it's like you don't want to do this, is what I'm saying. Like this would be, it's possible, but you want to avoid it if there's a much easier option. So how you can avoid this is you can just switch the order of integration, right? And how we switch the order of integration is instead of viewing this as being vertically simple, we can view it as being horizontally simple, right? Because like the lower bound with respect to x is always given by 0. And then the upper bound with respect to x is always given by y is equal to x over 2, which you can write as x being equal to 2y, right? So we don't want to view it as being vertically simple. Let's see what happens if we view it as being horizontally simple. Right. And you can't always go between like horizontally and vertically simple. Just because something's vertically simple doesn't mean it's going to be horizontally simple, but it works in this example, right? So for viewing things as being horizontally simple, what this means is we're going to be integrating with respect to x first, and then we'll be integrating with respect to y. And then this will be e to the y squared. So the function doesn't change at all. It's just the order in which you're going to be doing the integral. And so if we're integrating with respect to x first, our bounds should be functions with respect to y. And so as I was saying before, like the lower bound with respect to x is always given by x is equal to 0 here. So this is the lower bound. And then the upper bound is always given by y is equal to x over 2. We want our function to be in terms of y. And so what this means is we want to rewrite this as just being like, you want to solve for x here. So you just multiply both sides by 2 to get x is equal to 2y. Right, so that means that the lower bound with respect to x is given by 0, and the upper bound with respect to x is given by x is equal to 2y. Right, so this is the scenario we're in. We're in this case right here, right? So, right, the functions should be functions with respect to y, and it should be bounds on x. And then with respect to y, you just need to note that the smallest y value, so these are going to be constants, the bounds for the second integral y. The lower bound is going to be given by y is equal to 0. And then the highest y value is y is equal to 2. So we're just bounded from 0 to 2. And so now this is a much easier integral to compute, at least initially, right? Because if we want to compute the integral of e to the y squared with respect to x, we're just going to treat this as a constant, right? So like this first integral is just going to be equal to the integral from 0 to 2 of x times e to the y squared. And then this is going to be evaluated from 0 to 2y. And then we'll have a dy afterwards. And so you plug in x is equal to 2y. And then you subtract by what you get when you plug in x is equal to 0. If x is equal to 0, the whole thing just goes to 0. So you just need to see what happens when you plug in x is equal to 2y. So this becomes 2y times e to the y squared dy. And now we have something we can play with, right? Like we can use u substitution to find what this integral is going to be, right? If we let u be equal to y squared, if you take the derivative, it just becomes 2y. And now we have an easy integral that we can compute. So we can let u be equal to y squared. Du is then going to be 2y dy. And so this is going to be equal to the integral of e to the u du. So it simplifies very nicely. I'm just going to change the limits of integration by plugging in, like if we plug in y is equal to 0 into u, this will become 0. If you plug in y is equal to 2 into this, you get 4. So you get 2 squared, which is 4. So this ends up just being equal to e to the u evaluated from 0 to 4, which is equal to e to the 4th power minus 1. Right, so you can see, like, even though, like, if you were to go through with this process, like, you will end up getting the same answer regardless, but you can see this one is far easier than going this route right here. So there's sometimes a tremendous advantage to being able to kind of reorient your interpretation of the integral, or like the region in which you're integrating over. It's like this one is pretty straightforward. This one's incredibly difficult, but they're the same thing at the end of the day. Any questions about this example? Yeah, and I will say, like, whenever I'm computing these double integrals, my hunch is always to view it as being vertically simple, just because I think it's more natural to think about things as being functions of x instead of being functions of y. But sometimes it kind of forces your hand, like in this example. So you do need to know how to go from one to the other. Okay, I think it's just like a bunch of examples today, pretty much. So there's 2 more examples on the next page, and then there's an example on the last page, or I shouldn't say last page, but I think on page 6 that I want to go through. Okay, so this example focuses on the most difficult part of these integrals, which is just setting them up in the first place. So for this example, it wants you to sketch the domain of integration, which is denoted by d, corresponding to the following integral. So it already tells us what we're integrating over, and it just wants us to sketch what the domain is going to be. And then what it wants you to do after is it wants you to change the order of integration and then evaluate. So instead of doing dx, dy, it wants you to do the integral with respect to dy and then dx afterwards. And so how we can think about this is the domain as written. So this is our domain D. So what it's telling us is that let's go from outermost to innermost. So we have that this dy corresponds to the outermost integral. It's the second integral. So this is telling us that y is going to be bounded between 1 and 9. Right, so we have 1 is less than or equal to y is less than or equal to 9. That's what this integral tells us. Again, the second integral, the outermost integral, corresponds to the outermost variable here. And then we're also told that x is bounded between the square root of y and 3. So we have the square root of y is less than or equal to x is less than or equal to 3. And so let's think in terms of what's going on with x here. Right, so if we have, like, what this is really saying is, like, we have a lower bound with respect to x, where we have that the square root of y is equal to x. And I feel like most people, myself included, like to think in terms of, again, functions of x instead of functions of y. Like right now we have a function of y and we want to think in terms of functions of x. So what we can do here is we can just solve for y. And all you need to do to solve for y is just take the square of both sides. So this is really saying that we have y is equal to x squared. And so in terms of what our picture is actually going to be looking like here. So this is the graph we're looking at. And so this is going to be, so we're told that y is bounded between 1 and 9. So that's going to be this part here. This is like the 1 to 9 part. And then we also know that y is equal to x squared is involved. And so you need to think in terms of like what value of x do we need to plug in to make sure that, you know, y ends up being equal to 1. That's going to be x is equal to 1. And then we also know that x squared is equal to 9 when x is equal to 3. This will be a little bit off, but now we can draw, like, so that means we have the following curve. Right, so I'm just drawing the curve like y is equal to x squared. Right, so we have this curve here. And so we're pretty much almost done actually in sketching the domain of integration here, right? And so the only thing we also need to take into account is like, well, like we have like x is bounded by x is equal to 3. And then we also have that y is bounded by 1. So we have something like this. So this is like the area or the region of, this is D, right? This is the domain of integration that we're looking at. I feel like maybe I didn't do the best job of explaining what was going on. Like the main idea is you just need to determine the relationship between x and y, which can be obtained by looking at this inequality. And it's easier to think in terms of y and x. So you can say this is, you can also say like y is, like this is the same thing as saying we have that like x is equal to the square root of y. So really I was just drawing like the square root of y here and using the fact that the upper bound of x is always given by 3, and that the lower bound of y is given by 1, and the upper bound is given by 9. Right, so in rewriting our domain D with these new features, you can reinterpret it in the following way. So you can also think of D as being just the region where x is bounded between 1 and 3, and then where we have that y is bounded below by 1, and it's bounded below by x squared. Right, so these describe the exact same region. They both describe what we have here. One's a function of x, or one's a function of y, and then the other is a function of x, but they're telling you the exact same thing. Okay, so this is how you can switch the order, right? So if you wanted to switch the order of the integral that we have here, we can use this interpretation rather than this interpretation. And so this integral we have up here that we started off with is the same thing as the following double integral. It's the same thing as going from 1 to x squared with respect to y, and then going from 1 to 3 with respect to x. And then you have what, like x times e to the y. Right, so these two integrals are the exact same. We just flip the order of the integral, which meant that we have to change what the bounds are going to be for both of them. And now this is like the easy part is actually computing what this integral is going to look like. Or for the most part, I mean, maybe this one's, I don't know. You might have to use substitution for this, but it's not so bad. Right, so if you wanted to compute this integral, so the first integral with respect to y over the integral from 1 to 3 of x times e to the y, and this is going from 1 to x squared dx. So this is going to be equal, so you have to use substitution, but it's not too bad. This is like x, so this will be e to the x squared, and then that will be minus just x times e, like we have here. And so I'm not going to go through the details exactly. So, I mean, for this, you can split it up into two integrals, like the difference of two integrals, where you let u be equal to x squared. So you get like a 2x, and then so you have like a 1/2 times like e to the u, blah, blah, blah. So let me just write out what this ends up being equal to. So this ends up being equal to the following. So if you go through these steps, which I'll write it out in more detail on the solutions, but you go through the steps, you use substitution, you end up getting that this is going to be 1/2 times e to the 9th power minus 9 times e. So the interesting part isn't really computing the integral or evaluating the integral itself, right? This is like a Calc 1 problem. It's more so like what I'm interested in making sure you know how to do is this part here. Everything else is kind of like, okay, now do the routine part. Okay. Any questions about this example? Either part, but maybe like this part. Any questions about what's going on? Okay, and it'll be more clear. Like the more practice you get, the more clear it will get. It won't be too bad if you get enough practice. Okay, this next example. So I think there's just two more examples I want to go through. If I have time, I'll go through the average value problem on the next page. But this example, it kind of harkens back to what we were doing in the beginning of Calc 2 last semester when we were looking at the area between two curves. So to find the area between two curves, you take the integral, and what you do is you subtract the upper curve from the lower curve and then integrate that. and that would give you the area between the two curves. And so there's no reason why we can't just use the exact same logic to find the volume between two surfaces, which is exactly what the next example is telling us. So for this example, it wants you to find the volume of the solid bounded above by the paraboloid given by z is equal to 8 minus x squared minus 9 squared. So that's this thing right here. And then it's bounded below by the paraboloid given by z is equal to x squared plus y squared. So it's what's pictured here, right? And then we're working over the domain where d, it's just the, it's not the unit circle, but like x ranges from -1 to 1. And we have that y is bounded between -1 and 1. So you don't have to do anything fancy with respect to finding the domain. Like we're just integrating over a rectangle. So you don't have to do any of this like, you know, like horizontally or vertically simple trickery, I guess. We're integrating over a rectangle. So the like setting up the integral itself won't be that bad. Right. So if we want to find the volume, like what we're really doing is like just finding the volume of the solid between the two surfaces. So we have this volume here. This is going to be equal to this double integral. And so again, we're just integrating over this rectangle that I'm highlighting in red. So you don't have to do anything fancy. Like the limits of integration are just like x ranges from -1 to 1 and y ranges from -1 to 1. So I'm just going to integrate with respect to y first. Though you could integrate with respect to x first. It doesn't make a difference. And just like in Calc 2, all you do is you just take the larger surface. So this is going to be like this 8 minus x squared minus y squared. And you subtract from it the lower surface that you have. So you subtract by x squared plus y squared. And then I'm going to integrate with respect to y first, and then I'll integrate with respect to x. Right. So now you can just, once you're done setting things up, the problem itself really isn't that bad. This is the integral from -1 to 1, integral from -1 to 1. So we have a minus x squared. So this is going to be 8 minus 2x squared. And then y squared minus y squared will be minus 2y squared. This is going to be dy dx. And now this is just a polynomial, right? So computing the integral of this is it's pretty straightforward. It just takes a little bit of writing. Right. So if we integrate with respect to y, this is going to be 8y. We treat x as a constant, so it'll be 2x squared y. This will be minus 2 over 3 y cubed. This will be evaluated from -1 to 1 dx. So you plug in x is equal to, or you plug in y is equal to 1. Subtract by what you get when you plug in x or y is equal to -1. So you end up getting the following, just skipping some of the tedious algebra. This ends up giving you 16 minus 4x squared minus 4 over 3. And I mean, you could combine these terms with one another because they're both constants, but I'm not going to bother. I'm just going to leave it like this. And now you integrate with respect to x. So this is going to be 16x minus 4 over 3 x cubed minus 4 over 3x evaluated from -1 to 1. And so you can plug in x is equal to 1, subtract by what you get when you plug in x is equal to -1. And this ends up giving you the number of 26 and 2/3. So 26 and then 6 repeating. All right. So, I mean, if you know how to do like finding the area between two curves, finding the volume between two surfaces, it's the exact same idea over again. That's what the takeaway from this example is. It's the exact same thing. There's no difference. The only difference being like we have a double integral now instead of a single integral, right? So you just do the upper curve subtracted by, or the upper surface subtracted by the smaller surface, for the exact same reasons why you did it in calculus 2 to find the area between two curves. Any questions about this example? Okay. Yeah, so there's like another application we talked about in calculus. Oh, I think I have it right now. So in general, what we just did, like the volume of a region between two surfaces Z1 and Z2, where Z2 is greater than Z1, is always going to be just be given by the difference given here. So it'd be Z2 minus Z1, the double integral of it, assuming Z2 is greater than Z1. Another application we looked at of integration in Calc 2 was finding the average value. We saw that it ended up being equal to the following formula. Similarly, you can find the average value of a multivariable function by using integration as well. So like this denominator of b minus a, if you go up in dimension, instead of looking at an interval, you're now looking at a square. So instead of looking at the length of an interval, you're now looking at the area of your square. Or I should say, I mean, this doesn't have to be a square, but in the simplest aspect or simplest case, it is just a square. So like the average value ends up being 1 over the area of your domain times the double integral of your multivariable function. So these two formulas, I mean, they're pretty much the same thing, just one accounts for a higher dimension. So I'm not going to go through this example unless I have time at the end of class, or I might do it in the beginning of tomorrow's class. But what's more important is this next idea. So let's skip page 5 and we'll just go into page 6. And I think this should carry us out until the end of class, because like this next example requires a little bit of thinking. Okay. And so we're going to be thinking about decomposing domains into smaller domains. And so we kind of did this already in Calculus 1, right? Like in Calculus 1, if you had, like this is the idea, right? If we have like this interval, if we had like an interval, we have like 3 numbers. I'm trying to think of how to explain this, right? If you have 3 numbers, A is less than or equal to B is less than or equal to C, and we wanted to think about the integral from A to C of f of x dx, you can decompose this integral into 2 smaller integrals by using the fact that we have a number b that's between a and c, right? So you can rewrite this integral as being the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Right, so we took an integral that's in terms of a larger interval, so the one from a to c, and we were able to rewrite it as the sum of 2 integrals over a smaller region. These 2 things are the exact same. And so we're going to be doing the exact same thing, except for double integrals now, right? So if you look at this picture, what we're going to be able to say is that the integral over the entirety of this region D, which is represented by this double integral here. So like the integral over this entire region is the same thing as doing the double integral over D1, which is this integral, plus the integral over D2, plus the integral over D3, plus the integral over D4, D5, however many like partitions you want to use, right? So like what we're saying is this double integral over the entire domain is the same as doing the sum of the double integrals over these smaller regions. Where we're making the assumption that D is the union of like this D1, D2 up until Dn, and that they don't overlap except possibly on the boundary. Okay, so this is something that will come in handy for this next example, but also like other examples that we work through in the future. And so this example, eventually, like we'll introduce theory that will make it so this problem's very simple. Namely, by using polar coordinates, we'll be able to make this example really easy. But we don't know how to integrate over polar coordinates yet. So we're stuck with just using this idea right here. So for this example, it wants you to evaluate the double integral of x over the region D, where D is the following, it's like half of an annulus. So like an annulus is something that looks like this. Oops. Looks like this. We only have half of it, so it's like half of an annulus. It wants you to integrate x over this domain that we have here. Right, and it's kind of hard to think about like how to go about doing this. Because it's like hard to describe what this region D is going to look like, right? Like eventually we'll introduce polar coordinates and we'll be able to think in terms of like, well, we have like a semicircle here of radius 1, and we go onto a semicircle of radius 2. So like r is bounded between 1 and 2, and the angle goes from minus pi over 2 to pi over 2. So in terms of r and theta, if we were thinking in terms of polar coordinates, we can easily rewrite this integral. but we don't know how to do that yet. And it's trickier than I'm making it sound. And so we have to do something clever to figure out like how are we going to write out this domain of integration that we have, right? Because it isn't like, it's not vertically simple as we have written, right? Because the lower bound changes from this curve initially to this curve later on. And then similarly, it's not horizontally simple because the lower bound is changing, right? From 0 to this curve here, and then to this, like back to 0 here. So we have to do something clever to figure out how we're going to integrate this. And I guess I'll ask you, does anyone have an idea? Using this idea of kind of splitting up or potentially thinking about this as being part of a larger domain, does anyone see the trick in terms of like how we can kind of think about this domain into something that's easier to integrate? It's kind of a hard question, but does anyone see? Yeah, so we can think about it in the following way. And so instead of thinking in terms of this semi, like this half annulus, we can think in terms of first, so just drawing the exact same axes over again. So this is like -1, -2. This is 1, 2. We can think first in terms of what we have here. Like, what if we filled in what we have here, right? This is what I'm getting at. Like, what if instead we filled in this part, in which case we would get this semicircle of radius 2. And then to go from this semicircle of radius 2 to what we have here, you can subtract by the semicircle of radius 1. So it's like we're looking at this semicircle, and then we're subtracting from it. So this is like a subtraction sign. The region where it's just the semicircle of radius 1. Right, so this part right here. Right, so all we're doing is like we're taking this semicircle of radius 2, and then we're going to subtract from it the semicircle of radius 1, and that will give us the region we have here. So what we want to do is we'll integrate over this semicircle, which is horizontally simple, and then subtract by the integral over this smaller semicircle, which is also horizontally simple. Right, so what I'm saying is that this double integral over d of our function x dA, let me describe this as being d2, and then this we can describe as being d1. This is really the equal to the double integral over d2 of x dA subtracted by the integral over what we're carving out. So like this d1 x times dA. Right, so we don't know how to compute this directly, but we can compute this, right? Because it's horizontally simple, and we can compute this because it's also horizontally simple. So we want to compute these two integrals and then find the difference between the two. And that will give us the answer for what this one is going to be. Okay, and so to determine what exactly is going on with the integral over d2, what we want to do is we need to find out what this curve is equal to, right? We see that x is bounded below by x is equal to 0. So we have 0 is less than or equal to x is less than or equal to something. And so we want to make use of what we know about circles. So this is a circle, like it really is, it's like a semicircle of radius 2, right? So we can think about a semicircle of radius 2 in the following way. So this is really x squared plus y squared is equal to 4. And then we're just assuming that x is always greater than or equal to 0, which ensures that we actually get a semicircle. And now we can solve for x to determine what the upper bound is going to be, right? So this tells us that x squared is equal to 4 minus y squared. And then if you take the square root of both sides, this implies we have x is equal to the square root of 4 minus y squared. And when you take a square root, usually it's plus or minus. But again, if you look at our region, x is always positive. So that means this is going to be the positive square root. If we had the other situation, like if we reflected across the y-axis, we would have to assume that x is going to be minus the square root instead, which would change things. So this curve that we have here, this is the curve x is equal to the square root of 4 minus y squared. And so this gives us the upper bound with respect to x, right? The upper bound is 4 minus y squared, right? And so now we can integrate, right? Now we know how to set this up. So this integral over d2 of x, this is equal to the following double integral. So x is bounded between 0 and then the square root of 4 minus y squared. And then we have that y is bounded between -2 and 2. So this goes from -2 to 2. And then we're just integrating x, and then we're first integrating with respect to x, and then integrating with respect to y. All right, so now it's just a matter of computing this integral. So this is going to be equal to the integral from -2 to 2 of 1/2 of x squared bounded between 0, then the square root of 4 minus y squared dy. You can bring the 1/2 outside of the integral. So this is 1/2 times the integral of -2 to 2. If you plug in the square root of 4 minus y squared into x squared, you just get 4 minus y squared. If you plug in x is equal to 0, it just becomes 0. So you just get the integral of 4 minus y squared. And now you just have to integrate this. So this is going to be 4y minus y cubed over 3. Then you plug in y is equal to -2 to y is equal to 2. If you plug in 2 and then subtract by what you get when you plug in -2, this will be 16 over 3. Right, so I'm going to move this down a little bit. Right, so what we just found is that this first integral is equal to 16 over 3. So that's the first part. Now we have to do the exact same thing with this smaller disk that we have. But it's pretty much the exact same process over again, right? The only thing that will change is instead of being like the square root of 4 minus y squared, this number 4 will be different. Before I continue, does anyone have any questions about like what we're doing or what we just did, how we computed what we just did? So I think if you can understand this example, setting up other integrals, at least in 2 dimensions, won't be too bad. Okay. Right, so this is the integral with respect to the semicircle of radius 2. Now we just do the exact same thing over again. So I'm going to kind of circle this off. So this was finding the integral over d2. Now we just do the exact same thing over d1, running a little bit out of space. Right, so the idea is the exact same here, right? So again, we have something that is vertically or horizontally simple, right? We have x is bounded between 0 and something else. The logic is the exact same. So this is really a circle, like a semicircle of radius 1. So you have like x squared plus y squared is equal to 1. This ultimately ends up being equal, or giving you x is equal to the square root of 1 minus y squared. So that's really the only difference that ends up occurring. So this ends up being less than or equal to the square root of 1 minus y squared. And then we also have that y is going to be bounded between -1 and 1 instead of -2 and 2 like we had last time. And so now we just have to compute this double integral, which is again pretty much the exact same thing. So this is over d1 x times dA. So this becomes the double integral of x, and then it's going to be dx dy, where x is bounded between 0 and the square root of 1 minus y squared, and then y is bounded between -1 and 1. So the computation is pretty much the exact same thing. So this ends up being 1/2 times the integral from -1 to 1 of 1 minus y squared, just like we saw in the previous part. And then if you integrate this, this will be equal to 1/2 times y minus y cubed over 3, evaluated from -1 to 1. And if you plug that in, it ends up being equal to 2 over 3. So this is the integral over the larger region, and then you subtract by the integral over the smaller region. And so this is going to be 16 over 3 minus 2 over 3 is what we just computed. And so this integral over the annulus is this the difference between these two integrals, the integral over these two regions. So that's just going to be equal to 14 over 3, which is equal to 4.67. I'll write it like this. So if you know how to do this problem, like setting up the integrals for this problem, you're in good shape with respect to these double integrals. Eventually, like next class, we're going to be going into triple integrals, which makes things a little bit more difficult. But if you know how to do this, you're pretty good with respect to double integrals is what I would say. Any questions about this example before we finish class? Okay. I usually have an office hour at 2 o'clock today, but it's going to be canceled. So I don't have an office hour today. If you have any questions, you can email me. And maybe I'll have like an office hour at 2 o'clock tomorrow instead. Yep, have a good one.